Alright, so today we'll start our discussion on a topic known as infinite series. And over the next few videos, we'll be delving further into the various intricacies of this subject. So the first thing we're going to talk about is something called the power series. And so that's going to be the focus of this video. But because this is the first time I'm introducing what the notion of an infinite series is, let us define the infinite series. So definition of infinite series. All right, so what an infinite series is an infinite series is an expression of the form a1 plus a2 plus dot 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 plus an plus dot dot dot. And basically it's a series of us summing up a lot of different terms, and this can be compactly written as k is equal to the sum from k equals 1 to infinity of a sub k. And so the reason why it's an infinite series is because the number of terms that we're summing up in this series of terms is infinite. So you might have seen different series before that are finite series, like for example, so some finite series that you might have seen before is sum up the terms from 1 to some value n, and you know that this is just the sum of n, where or sum of k, where k is equal to 1 to n, and that would converge to the value n times n plus 1 divided by 2. But now an infinite series is where we don't have a particular ending value n. In fact, the upper limit on our range is some infinite sum. And so because of this infinite sum and in the infinite number of terms in our series can either converge or diverge. And we've seen this like converging or diverging behavior when we've looked at improper integrals, and that's just what happens when we like tend towards infinity. Either our things blow up, or either they converge to a certain value. So basically the idea is, if our infinite series, so if this infinite series, so the sum from k to infinity of a to k, equals some value s, so some finite value, then we say that the infinite series converges, right? And on the contrary, otherwise, the series diverges. So one of the biggest questions of series are whether these series diverge or converge, and in order to prove that they converge, we'll get to methods to prove that they converge. But if a certain series converges, then that means that the sum of that infinite series comes up to some finite value s. And this is pretty consistent with the different definitions of convergent behavior that we have seen before. And so hopefully this definition and this introduction to what an infinite series is makes sense, and let's just continue on this path. So the first question is, so question 1, and this is sort of like a trick question. It's more like a definition question. So does this series of alternating plus ones minus ones converge or diverge? And you might be tempted to say that, okay, we can kind of pair up our alternating plus ones and minus ones, and we see that all of these are just 0. And you might be tempted to say that, okay, on the infinite case, we're just summing up a bunch of zeros, and so yes, it would converge. But in fact, we can't really guarantee that we'll have pairing. So cannot guarantee these pairings that we made in order to get to like the zeros. And because we cannot guarantee these pairings, we cannot guarantee the fact that we can associatively add up each of these pairs and then add up the resultants of the pairs. And so we cannot guarantee that we can simplify after pairing the ones with the negative ones and adding up all the zeros together. And because of that, as a result, this series diverges. So this is like kind of, don't worry if it's like kind of hard to get your like wrap your head around, but the like main takeaway is that because you can't really guarantee the order in which you can add up these sequences together, you can't guarantee the pairings as well. And this the proof of like the fake proof of showing that this converges would require us to pair up terms together, and we can't really do that. So because of that, this series must diverge. Now let's look at another series. This is 3 over 10 plus 3 over 100 plus 3 over 1,000, and then it keeps going on, plus 3 over 10 to the n. And now does this converge or diverge? And so the first thing you might recognize is like through your past experiences in algebra is that if we look at these sequences, they're all like the next term is just the previous term. So a of n plus 1 is simply a of n times 1 over 100. And so this resembles a geometric sequence. And more specifically, it represents an infinite geometric sequence. And we know that when the common ratio of an infinite geometric sequence is, so this is r, and when r is less than 1 or greater than negative 1, it converges. And therefore, because 1 over 100 is between those two bounds, we have convergent behavior. And so this required our knowledge of a geometric sequence in order to determine whether the series converges or not. And that's that's one of the most basic sequences or series. And as we'll cover infinite series more in detail, we'll see different types of series and see what ranges they converge in. But one of the most basic types of infinite series is the introductory geometric series that we have seen. And we know that a geometric series converges when we have the specific ratio between negative 1 and 1. And so this was an example of a geometric series. And just in case you guys don't remember geometric series, let me introduce them here. So a geometric series is a type of infinite series, and it comes in the form of a plus a times r plus a times r squared plus a times r cubed. And then you keep adding up, or our next subsequent term is just taking the previous term and multiplying by r. And compactly, this is just written at a times r to the power of n minus 1 from n is equal to 1 to infinity. And this geometric series converges to a divided, where a is the first term, a divided by 1 minus r if the value of the absolute value of r is less than 1. So that would mean r is greater than negative 1 and less than negative 1. Otherwise, when r is greater, or the absolute value of r is greater than or equal to 1, it diverges. So hopefully this series is review and these facts are also review. But just if not, then this is the property of like the first sort of infinite series that we will see. And so the reason why I introduced the geometric series first is because hopefully it can kind of like map the idea of an infinite series to something you guys have already seen before. And this range where we are converging is called the interval of convergence. So oftentimes with infinite series, we're kind of concerned with what ranges do we get convergence in, and that range is known as the interval of convergence. And for a basic geometric series with the ratio r, whenever r is between -1 and 1, that is where we have an interval of convergence. So let's just do some practice with geometric series. So the first one is, so for each of these, we want to determine whether it converges or diverges. And so let's get into it. And if it converges, because it's a geometric series, we kind of know a way to find the sum, so we should also find the sum. So this is the first problem. 3 times 1/2 to the power of n minus 1. And if you notice this original definition of geometric series, it's literally the same form. And we see that 1/2 is less than 1. And so we know that this converges, and we can plug it into our infinite geometric series formula and simply get 1 or 3 divided by 0.5, which is equal to 6. So that's what we get converges to. Now the next series is 1 minus 1/2 plus 1/4 or plus 1/4 minus 1/8 plus negative 1/2 to the power of n minus 1. And so clearly, like this formula over here, so the first thing I usually look at is this general formula. And this general formula kind of follows the geometric series with the first term as being 1 and the common ratio being negative 1/2. And negative 1/2 is between -1 and 1. And so this should converge as well. And the value it converges to is simply given by this sum formula, which is just 1 divided by 1 minus 1/2. And that is simply equal to 2 over 3. Now, let's continue working with the 2 more examples. So this is example C. In example C, we have the sum from k is equal to 0 to infinity of 3 over 5 to the power of k. Now, this is not exactly in the form that I represented geometric series with, because we have a starting value of k is equal to 0. But we can always convert it into that form by like kind of taking out the k equals 0 term. And when k is equal to 0, this is just 1. And so it's simply 1 plus the sum of k is equal to 1 to infinity of 3 over 5 to the power of k, right? And so two things, like it's just this geometric series with ratio 3 or 5 with the first term 1. Or you could just treat this as a separate geometric series and add 1. But either one works. I'll just do the former. So 1 is the first term divided by 1 minus 3 over 5. And then that simplifies simply to 5 over 2. And obviously, because we got a value it converges to, this series converges. Now let's do one final example. In this example, we have the series pi over 2 plus pi squared over 4 plus pi cubed over 8, and it keeps going. And so if we see the common ratio is kind of clearly pi over 2. But notice how pi over 2 is greater than 1. It's because 3.14 divided by 2 is greater than 1. And because of that, this series is a geometric series, but since the r value is greater than 1, it diverges. So hopefully that was good review into geometric series. And now let's get into what the topic of today's video, the main topic of today's video is, and that is the notion of a power series. And before I get into that, just a quick aside, notice how how a geometric series kind of looks like 1 plus x squared, and it keeps going, plus x to the n. And we got that plus x to the n plus like for infinitely many terms, the same left hand side is equal to 1 over 1 minus x only on the domain of convergence, right? So this is a really interesting result where we have an infinite series being able to, which we can represent as like some non-infinite term, but this equality only holds true for a certain domain. And in case of the geometric series, it was between 1 and -1. And so given that, let's go back to the power series. And so a power series is an expression in the form for the sum of n is equal to 0 to infinity of c of c sub n times x to the power of n. So that's simply c0 plus c1 times x plus c2 times x squared all the way cn times xn, or cn times x to the power of n, and then we keep going for infinitely many terms. And so all this sum means is that we're representing our power series is a series where we have some constant multiplied by some power function, and the degree of that power function starts at 0, so that's why we have this constant term with no x term, because the degree here is 0, and then it keeps going on. So we're basically adding up these the power series, just a summation of infinitely increasing degrees of polynomials. So all of these are power functions, so x squared, etc., and they have different constants attached to it, and we're creating the sum of that, and that series is the power series. And so this in this form, the series in the form above is centered at x equals 0. Now, another formation of this power series is the sum from n is equal to 0 to infinity of c of n times x minus a to the n. Now this is a power series centered at x is equal to a. So all we have done, the only difference between the top series and the bottom series is now we are recentering our power series at some value a. And the notion of the center is simply that when we plug in x is equal to a, notice how all of these terms will essentially zero out, and all we're returned with is that initial constant value of c0. And that's the whole idea of like the centering. So if we have any like minus value associated with it, then we're centering it at a non-zero constant. And like notice how both like this bottom power series, if we are centered at 0, then it would just become like it would just simplify to the top one. So this is just a more general power series that we have represented. And one thing that's like interesting, so like I started off with a set aside on a geometric series. A geometric series, if we look at it, is just a special representation of a power, or it's just a type of power series, right? So geometric series are a type of power series, because in the geometric series, our constant terms is simply the first term, which in like this case was 1, but it could just be like the first term, like an a term, and then the x term is simply whatever our ratio is, and then we always keep increasing the power of that. And so the geometric series is a type of power series which converges, like we already saw, if x is within -1 or 1, which converges when x is less than -1 and, or sorry, when x is less than 1 and greater than -1. Right, so we have seen the relationship between geometric series and a power series, and so power series encompasses a lot more different types of series, and a geometric series is just one type of that. Now, since this is related to calculus, let's look at how we can find a power series by differentiating and integrating. So power series through differentiation. So we already know that the power series, or 1 minus 1 over x is equal to 1 plus x squared, when obviously, like, all of this is just, this equality only holds when this power series converges to 1 over 1 minus x, and we know that's only when x is between -1 and 1. So on the interval x is less than 1 and greater than -1, so this equality holds. Now let's find another power series to represent 1 over 1 minus x squared. So find series that represents this. And if we were to look at this carefully, if we were to look at the bottom thing carefully, we can see that if we were to differentiate 1 over 1, so d over dx of 1 over 1 minus x is simply equal to 1 minus x to the power of -2, and then we had the -1, and then now we have to differentiate the inner term through chain rule, so 1 minus 1 over x, 1 minus x, so that's another -1, and so that's simply equal to, we simply get 1 minus x to the -2, and that's simply 1 over 1 minus x squared. And so the derivative of the original of 1 over 1 minus x is this new power series, or is this new term that we want to find. And it kind of makes sense that if 1 over 1 minus x is equal to 1 plus x squared on this interval, then the derivative of 1 over 1 minus x must also equal the derivative of the series. So in other words, since d over dx of 1 minus 1 over 1 minus, or 1 divided by 1 minus x is equal to 1 divided by 1 minus x squared, d over dx of 1 plus x squared continuous, which is equal to d over dx of the sum of I is equal to 0 to infinity of x to the I is simply equal to the sum of I is equal to 0 to infinity of I times x to the power of I minus 1, and that's because this I over here represents a power, and then we just use the rules of differentiation. And notice how when we have I equals 0, this term just becomes 0, so we can rewrite this simply as the sum from I is equal to 1 to infinity of x to the power of I minus 1. And if differentiating in this compact summation notation is confusing, sorry, I forgot this I term, is confusing for you guys, then one thing that you could do is just differentiate all of these manually. So I would get 0 plus 1 plus 2x plus I would have 3x squared, and then try to rewrite whatever you see here into summation notation, and you'll see that that's the same thing as the sum from I is equal to 1 to infinity of I, because that's this term, and then we need that x term, but the x term kind of lags behind, where over here it's like x to the power of 0, and so if I is 1, then x to the power of I minus 1, so, and that's the same thing that we got over here. So either way works, and you should probably use whatever method feels more comfortable with you. But, so, the idea is, since d over ddx of 1 over 1 minus x is equal to 1 over 1 minus x squared, and 1 over 1 minus x on the interval from -1 to 1 is simply equal to this series, that means the derivative of this series should, or like intuitively it makes sense that the derivative of this series should equal to the derivative of whatever it converges to. So this is the derivative, and then that should be equal to this thing, because now we're just finding the derivative of two equivalent ideas. And although this was just like empirical, this is actually true. So what we saw before is something called term by term differentiation. And essentially what it states is that if we have some series f of x is equal to n is equal to 0 to infinity of c sub n of x minus a to the power of n, that converges for x minus a, the absolute value is less than r. So all this is saying is that we have some function that is equivalent to some series, and that series converges on some interval, and that's what this inequality states. Then the series obtained by differentiating the series for f term by term, and term by term just means as we increase whatever value of n there is, similar to what we did in the previous example. So the series for f term by term also converges on x minus a is less than r, and represents f prime of x on that interval. So what this theorem basically states is that if we were to take the derivative of the series term by term, similar to what we did before, whatever we get represents the derivative of whatever that series converged to. So remember the previous example, we had a series that represented 1 over 1 minus x, and that series was just I is equal to 0 to infinity of x of I. When we took the derivative of this term by term, so d over dx of that summation term by term is just the same as the d over dx of 1 over 1 minus x on, and this equality is guaranteed to hold at least on the interval our original series converged at. So in the case of this geometric series, we knew that this would converge on x between -1 and 1, and so this equality that the next equality we got by taking the derivative of both sides is also guaranteed to converge on those on that same interval. And so this is true for any general series. And one thing to note is this at least. There could be cases where the derivative of a particular series, whatever, or the derivative of a particular function, whatever power series represents that function, possibly converges for larger intervals than the original function itself. And I can't think of any examples off the top of my head for that, but that is a true statement. Now we dealt with differentiation. Now let's deal with power series and integration. So once again, we know that 1 over 1 plus x is equal to 1 minus x plus x squared minus x cubed plus minus x to the n, right? Now find a power series to represent ln of 1 plus x. Now we know like this, what this given formula gives us a pretty big hint of we want to integrate 1 over 1 plus x, because that will give us ln 1 plus x. So the integral of 1 over 1 plus x dx is simply equal to natural log of 1 plus x. and we don't need absolute values because we know that this original function, this original series only converges when x is between -1 and 1. And in that range, ln, or then like 1 plus x is always positive, so I can just remove all absolute values. So that's the reason for that. I found the relationship between, if I call this f of x and the the power the function we want to find the power series for. And so similar to what we did last time, let's integrate the series as well. So we know that the series is given by the sum of I is equal to 1, or I is equal to 0 to the power of n of, or I is equal to 0 to infinity, sorry, of x, negative x to the power of n, and you can get that from this as well. And if we were to integrate all of these terms term by term, we would get something like n n plus 1, right? Negative x to the power of n plus 1 divided by n plus 1 minus, and then we need that negative to come out as well. So something like that. Oops. Right there. And this essentially, it becomes, well, okay, so over here we get negative x to the power of n plus 1, and then we have a negative sign that follows divided by n plus 1, and the sum from I is equal to 0 towards n, or infinity. So that's what the integrating the summation is, and let's see if we can try to simplify what this summation entails. So whenever we have a positive, also this shouldn't be n over here, this should have been I, so all of this is I. Whenever we have a even I, then we have a odd, this power is an odd power, and so this negative value towards an odd power will give out an odd value, but we're also multiplying by a -1. So what ends up happening is, on an even power, we get an even value. And so we can simplify this by just writing this as the sum of I is equal to 0 to infinity of -1 to the power of I times x to the power of I plus 1 divided by I plus 1. And this comes from like me just talking about how, just relating the even powers of I to whether the value is going to be even or odd. And if the summation notation is confusing, then another way that you could have derived this is through term by term finding the integral of all these values. So let me rewrite this over here. So we had this sort of, kind of series, and so the integral of this is x, the integral of this term is minus x squared divided by 2 plus x cubed divided by 3 minus x to the 4th divided by 4th, all the way times, right? So you have at least these first 4 terms, and this should help you generalize into this sort of series. And so notice how we have some, basically whatever this represents is equal to what I pointed out over here. So when x is equal, the first term is when I is equal to 0, so -1 to the power of 0 is simply 1. 1 times x to the 1 divided by 1, so that's x. The second term should have x squared, so that's when I is 1, and that we'll have a negative term associated with it, and then hopefully you see how these two terms are equal. But essentially, we got this new series that represents ln of 1 plus x. And similar to the term by term differential theorem we saw before, there's a term by term integration theorem. So the term by term integration theorem basically states something very similar. So if f of x is equal to the sum from n is equal to 0 to infinity of c of n times x minus 1 to the n. Notice how this is the general power series formula, and it converges, and for x minus a is less than r. And saying that it converges for the specific range of values is the same thing as saying that this equality holds for these specific values. Otherwise, an infinite series cannot be represented by just a regular regular non-infinite function. So back to that. Then the function obtained by integrating the series term by term converges at least. So again, we have that at least. It could converge for more values, but we're guaranteed for at least the same values as our original function converges for. So that, and also represents the integral of f of t dt. So we just replaced it with a dummy variable here, but f of t dt on that inter. So essentially, this says basically an analogous thing to what we saw in the term by term differentiation theorem, where all it's saying is that if we have this equality of f of x to some infinite series, if we integrate both sides, the equality will hold for at least the interval where the original equality held. And so that was an introduction to power series and how they're related when we differentiate and integrate, and how a geometric series is an example of a power series as well. And hopefully as we do more videos, we can get better with different series and reason about them better as well.